test tomorrow covering, well, you can kind of guess what most of the test is going to be. Derivatives, the rules, exponential, logarithmic, trig. Okay. Which these were chapter 4 and chapter 5 on the Think Well material. Then we looked a little bit at implicit differentiation. A couple sections on that, I think chapter 6, which they have very small chapter on that stuff. And then the applications, the first section of chapter 7 on position, velocity, and acceleration. So we've covered a lot of ground. As you would expect, most of the test will be this right here. In fact, it starts out, find the derivatives for the functions in problems 1 through, can't remember exactly how far, but it's going to be well over half of the test will be derivatives. Maybe 12, 13, 14 problems. Okay. And it's going to be all kinds of different types of functions, dealing with power rule, product rule, quotient rule, chain rule. Then we get into all those special functions with the trig functions, exponential functions, logarithmic functions. Okay. And just lots and lots of finding derivatives. Now, let's take a look at some specific details. The derivative rules. Now, the most basic one is your power rule, but sometimes those end up being the hardest because we've got to change the form of the function we're looking at to get it into x raised to some power. And something like that, we would need to change to what? Okay, x to the negative 3. Then we're ready to take the derivative. Okay. Or maybe something like 5th root of x cubed, we would have to do what to first? Okay, x to the 3/5. Now, both cases here, I have not taken the derivative, I've just rewritten the form algebraically, so we can use the power rule on it. So sometimes, especially when we first start looking at these, that's the hardest part about the power rule. Okay. Then we have the product rule. I'll just kind of show you in general. Product rule is what?
First times the derivative of the second plus the second times the derivative of the first.
Okay. So the first times the derivative of the second plus the second times the derivative of the first. Now, the order on this really doesn't matter. Most students start with this, but the second part, sometimes they'll rewrite it and say plus the derivative of the first times the second. Okay. Either way, doesn't matter. Because multiplication is commutative, we can rewrite the order. And in fact, you could start with the derivative of the first if you wanted to, because addition is also commutative. So just as long as one term has the derivative of one part times the other, and then vice versa on the second part. Oops. Helps to get the right one. We'd have, what, g prime times f. Okay. So order, not going to make any difference on what you start with. But the key there, something that you got to remember, it is not just f prime times g prime. More work to it than that. Usually in mathematics, things aren't quite as easy as we want them to be. So then next we have the quotient rule. And the quotient rule, now this one is very specific, and the order is important because we have a minus. Subtraction is not commutative. So we do start with the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Make sure you're squaring that bottom part. And again, this by itself, this is pretty straightforward, but then when we start throwing 2 or 3 rules embedded in themselves, it kind of gets a little more difficult. But those are your basic rules. I guess the other one we haven't talked about yet is the chain rule. I'm going to take the derivative of technically a composition, say the square root of the quantity x squared minus 4 or something like that. Okay. F represents the outside. So the chain rule says the derivative of the outside and then evaluated with the original function still on the inside. Okay. And then finally the last part times the derivative of the inside. And the most common mistake here is taking the derivative of f and the derivative of g, putting that derivative of g inside the derivative of f. That's not the case. We put the original g of x, keep that on the inside, and then multiply the derivative of g on the outside. Okay. I think next we had our, was it trig functions or exponential, logarithmic, whatever order, it doesn't really matter. Let's go ahead and look at the trig functions. And this is, you will need to know these. I'm not going to allow a note card or anything like that, but hopefully by now you know these. But there are some similarities between the trig functions. And let's go ahead and write down sine of x, derivative of that is cosine of x. Now the one kind of relating to that is derivative of cosine x. And what do we find for derivative of cosine x?
Negative sign.
Okay, negative sign. Sounds like all of you got that one down. Of course, those are the two easy ones, really, compared to the rest of them. Next, let's look at tangent. Derivative of tangent x is what? Okay, secant squared x. And then the derivative of cotangent x is? Okay, negative cosecant squared x. And then finally the derivative of secant x. This one's the kind of strange one where derivative of secant x is secant x and then times tangent x. And the derivative of cosecant x is what? Be negative and then cosecant x, cotangent x. Now, if you can remember three of these, the other three kind of follow. Not exactly equal, but have some very similar derivatives. First of all, which types of functions, types of trig functions has the negative on it?
The ones that start with Z.
Okay. Cosine, cosecant, cotangent. All of the what I call the co-functions, have the negative derivatives. Okay. And then, as we look at, well, of course, the sine and the cosine kind of go together. Just remember again, the derivative of cosine is the negative. Derivative of sine is just cosine. Tangent x, take a look at that one. We have the secant squared x. And then related to that, derivative of cotangent x. Again, first the negative. And then it's the square of cosecant rather than the square of secant. So tangent and cotangent, those derivatives have the squares of either the secant or the cosecant. And then finally, the one I have the hardest time with is the secant x. Derivative is, well, itself times the tangent x. And then as we relate that to the derivative of cosecant x, again have the negative, and then instead of secant we have cosecant. We're still looking at the same function, derivative of the function we start with. That function will be part of the derivative. And then the other second part to the cosecant is the cotangent. So those last two relate closely to each other. So hopefully that will help you remember which one's which. And if you can remember one in detail, then the related one hopefully won't be too difficult to remember the details on it. Okay. Now the derivative of the exponential function is what? Okay. This is that really hard one. Well, maybe not. This is my favorite function in the realm of calculus. Derivative of e to the x is e to the x itself. Makes life a lot easier. Okay. Now, we did look a tiny bit at other bases. For the test, I am not going to have like 2 to the x or something like that. It'll be strictly base e with the exponential, and also with the logarithms, just the base e for that as well. Derivative of natural log of x is? 1 over x. Now those are the basic formulas, and of course we saw a lot more than just what's the derivative of natural log of x. We saw it as a kind of combination with other functions. Some, not a lot of combination, but a little bit. There will be some that are several steps, okay, that last kind of compilation of derivatives, combinations of functions, those fun derivatives. There might be one or two that kind of that length. Some of them will be fairly straightforward. Some will be kind of medium, take 4 or 5 steps instead of just 1 or 2. And then again, there's going to be a handful that might take 6 or 8 steps to it. Those good old embedded chain rule inside another chain rule inside a quotient rule inside a product rule. Maybe not quite that bad, but possibly some combination like that. Okay. Now, one thing that not too many of you seem to grasp when we're dealing with the logarithms, we can change the form of that to make life a lot easier on us. Let's take a look at one in particular. Now, if we looked at this one and took the derivative in this particular form, it can be done, but it gets extremely messy. What can we do to this one to make it much easier?
Can you raise it all to the negative?
Okay. Well, before we even deal with the derivative, let's rewrite the logarithm using log properties. And so one of the biggest problems with the logarithms might be changing the form to make it simpler, taking the derivative. Let's go ahead and rewrite this, and we'll put it on top of the next page. And we have lots of steps to do even before we worry about the derivative. First thing we can do to make this a lot nicer. Okay, we have the log of something to a power. We can pull that power out in front and make it the 3 times the natural log of just this quotient. Now what can we do? Because of the quotient, the division here, we could rewrite this as natural log of the top minus the natural log of the bottom. Now, one thing you have to be very careful with, that 3 out in front needs to be multiplied by the whole thing. Okay, so don't lose that. Now, is there anything else we could do? We have 2 different logarithms here. Anything we could do to the first one to make life a little easier? We have a product, x times the sine of x squared. We can rewrite that as what? Natural log of the first plus the natural log of the second factor. And anything we can do to this last term? Actually, that's as far as we can go with that one. We cannot separate that into natural log of 3x minus the natural log of 4. Unfortunately, that doesn't work. But when we're multiplying, we can separate it into log of one plus the log of the other. When we're dividing, we can say the log of the top minus the log of the bottom. Okay. Now we're ready to take the derivative. So, I guess the derivative of this, we have this constant out in front, and we can kind of just look at one part at a time. Derivative of natural log of x is what? Okay, 1 over x. Now, careful with this next one. You might say, well, there's a power, that square we could pull out in front, but that square is not applied to the entire inside of the logarithm. That square is only applied to the x. We have the log of sine of something. Now, if we're squaring the sine, then yeah, we could pull that 2 out in front. But we're squaring just the inside of the sine, so we cannot pull the 2 out front. Which this makes it a little more interesting, a little more difficult to work with. But derivative of this term would be what? Okay, all right. Natural log, we'll have the 1 over the inside of the natural log. And then times derivative of the inside, which is our sine of x squared. What's the derivative of sine x squared? It would also be a chain rule. Outside of this part is sine, so derivative of the outside is what? Okay, cosine of what we have on the inside, and then finally times the derivative of the inside, which is 2x. So that kind of is an embedded chain rule. Chain rule on the natural log and then chain rule on the sine. Okay. Questions on that part of it? That, by far, that one piece is the hardest of all the pieces. And then finally this last one. Derivative of the natural log of this quantity. 1 over the inside times times 3 times the derivative of the inside. Derivative of 3x minus 4 would be the 3. Okay. And then, well, algebraically this could be written in about a million ways, but you get to this point, that's fine. Or possibly if there's a little bit of simplifying, this one there really isn't all that much simplifying you can do, but that would be a correct form of the answer. Okay? So with those logarithms, the properties can make finding the derivative so much easier. And I've noticed the ones I've seen, the worksheets I saw with the logarithms, some of you weren't doing the properties, or at least not as many as you could, and the derivative just got real ugly. This derivative's ugly enough the way it is, but can you imagine trying to do the derivative of the original? Okay. Questions? Okay, so now working with e to the power, it's a lot easier than the natural log. It's simply the derivative is e to that power and then times the derivative of that power, and we'll write it this way for now. Most of you can go without writing that step, but some of the exponents can get a little tricky, so just keep that in mind. You may need to do this kind of intermediate step, but yeah, this one be e to the 5x times 5 as your derivative. Okay. There's not really a lot of special properties that we have to use for e to some power because the derivative is so easy to work with. But definitely with the natural logs, there's lots of simplifying we can do before we try the derivative. Well, that kind of sums up our derivatives and all the fancy formulas and shortcuts. Yeah. For the bases, I will only give you base E on the test. Now later on, we may expect you to kind of remember, or at least be able to find what the derivative of 2 to some power would be. But for this test, I'm going to limit it to just the base E, logarithms, and the exponential. Okay. So this, like I said, there's 20 problems on the test, so the first 12, 13, 14 problems will be find the derivative. Okay. Now, the last part, we talked about the implicit differentiation, and you may have something like find dy by dx for some equation like this. Okay. Definitely using implicit differentiation. Okay. One big problem here, something we tend to forget, this right here would be a product rule. Okay. And since we're wanting the derivative of y with respect to x, that's also something you got to keep in mind. Okay. We may see it as dx by dy, but in this case, with respect to x, the derivative of x squared will just be the 2x. Derivative of this, well, product rule will be the first times the derivative of y with respect to x, and then plus the second times the derivative of the first, or let's just go ahead and do the derivative of the first and then times the second. So that right there would be the derivative of this part. And then what? What's our derivative of this one? Y squared, derivative, kind of think chain rule, power rule, we'd get 2y. Are we done? No, we're taking the derivative with respect to x, so the derivative of the, quote, inside, derivative of y with respect to x is your dy by dx term. Okay, and then, well, thankfully, the other side, derivative of 5 is 0. Okay. Then, a lot of these turn into more ugly algebra equations than anything else. Solving for dy by dx, we can move these two to the other side. And what we do with these, if there's two terms involving the dy by dx, we can factor that out. So we'll leave the x cubed and then minus 2y factor out our dy by dx, and then subtract the 2x and 3x squared y from both sides. And then to finish that off, we do what? Okay, divide by this factor. So dy by dx, we got our 2x minus 3x squared y all over x cubed minus 2y. Actually got that in there. So finding dy by dx using implicit differentiation. Also, we may have find the equation of a tangent line. Now, we saw a few more of those with our implicit differentiation. So maybe I'll just throw in a fairly straightforward one. Well, fairly straightforward. It's not going to be real nice. The point needs to be on the graph itself, but square root of 2 would be on our circle, x squared plus y squared equals 4. So do the implicit differentiation, then dy by dx in this case would represent what? Okay, since we're dealing with the tangent line, that represents the slope of the tangent line. Calculate dy by dx, plug in these numbers for x and y into the dy by dx, and that will give you the slope. And then the equation, now it may just be find the slope of the tangent line, or it might be find the equation of the tangent line. If it's the equation, then we have one more step. Plug it into your point slope form. And there would be the equation of that tangent line. And then the last thing we've looked at in this unit, position, velocity, and acceleration. We talked a little bit about this stuff earlier in the semester, but now relating it specifically to derivatives and being able to find the derivatives a lot easier than what we did at the beginning of the year. Position function, we use a lot of different letters to represent that. S of t, R of t, F of t, whatever, H of t. The velocity then would represent what? I guess a lot of times we'll call that v. How do we find the velocity function?
It's derivative of the position.
Okay, right. It's just the derivative of the position.
And acceleration is the derivative of the position twice.
Okay, right. Acceleration, a of t. Well, a couple ways to look at it. We could say it's the derivative of the velocity, or what we will call the second derivative of the position vector or function. So later on we'll kind of get into the more formal second derivative, third derivative, fourth derivative, but that's really what the acceleration is. We take the derivative of the position function, and then we take the derivative of that. So technically taking the second derivative of the position function. And then lots and lots of different questions that come about from position, velocity, and acceleration, just as the worksheet from yesterday. So make sure you're able to answer those types of questions. Okay? So tomorrow will be our test. You can come in early if you want or stay late. I don't restrict you just to an hour, but I know Monday, Wednesday, Friday you probably have classes either before or after or maybe both, but we can work the time around. If you can come in early, feel free to. I'll be in here at 8:30 tomorrow morning, so however early you want to come, and I'll be here until 12:30 tomorrow afternoon, so hopefully give you plenty of time.